Is it visible, my presentation? Is it visible, my presentation?
Yes.
Okay, thank you.
Okay.
So, our talk is about nearings and gap.
Yeah.
So, we decided that our section is applied algebra, so we need to provide more information about using computer algebra in our investigations. For example, we talked about gap and how it helps us in our study of our subject, for example, nearings. And so I continue. Nearings are generalizations of associative rings in which the additive group can be non-abelian and addition is connected with multiplication by only one distributive law, left or right. In this sense, local nearings are generalizations of rings. So I recall the definition of nearing. A non-empty set R with two binary operation addition and multiplication is a nearing if via addition is a group with neutral element 0, via multiplication is a semigroup, and only one distributive and at least one distributive law holds. For example, x multiple y plus z equals x multiple y plus x multiples z for all elements x, y, and z from a nearing R. Such a nearing is called left nearing. If axiom 3 is replaced by an axiom from right side multiplication, then we get right nearing. And the group R plus of a nearing R is denoted by R plus and called the additive group of R. And if an addition 0x equals 0 for all x from nearing R, then R is called the zero symmetric. Furthermore, R is a nearing with an identity I if the semigroup is a monoid with identity element I. In the latter case, the group of all invertible elements of the monoid R is denoted by R star and called the multiplicative group of R. Clearly, every associative ring is a nearing, and each group is the additive group of nearing, but not necessarily of nearing with identity. The question what group can be the additive group of nearing with identity is far from solution. The problem of finding the groups that can be additive groups for the nearing with identity is started from the late 1960s. One of the first results in this direction was obtained in paper Clay-Malone 1966, where it was shown that there exists a unique nearing with identity whose additive group is cyclic, and that in fact this nearing is a commutative ring. A study of local nearings was first initiated in a paper by Maxson 1968, and it was found that the additive group of finite zero symmetric local nearings is a P group. In other paper, but the same year, Maxson shown that up to n isomorphism there exists P-1 local zero symmetric nearings with elementary abelian additive groups of order p square, in which the subgroups of non-invertible elements have order p, that is, those nearings which are not near field. Together with the fundamental paper Sissenhaus 1935-36 and Clay-Malone 1966, a complete description of all zero symmetric local nearings of order p square is obtained. The dihedral group of order 8 cannot be the additive group of local nearing. This result from Maxson 1971. And the existence of local nearings on a finite abelian P group is proved in paper Maxson 1970. For example, it gives that every non-cyclic abelian P group of order P in power n more than 4 is the additive group of a zero-symmetric local nearing, which is not a ring. Also, it is established in our paper with Sisaka, 2012, that an arbitrary non-metacyclic Miller-Morena P group of order P in power n more than 8 is the additive group of some local nearring. Nearring with the identity and local nearring on Miller-Morena groups were studied in our papers 2012, 2011, and 2020. Boycott and Bauer in their preprint in 1998 classified all non-abelian groups of order less than 32 that can be the additive groups of a nearring with identity, and found the number of non-isomorphic nearrings with the identity on such groups. The package Sonata, the authors Eichinger, Binder, Ecker, Meyer, and Neubauer, this new version 2008. But first version of this package was in 1996 of the computer algebra system GAP contains a library of all non-isomorphic nearings of order at most 15 and nearings with identity of order up to 31, among which 698 are local. However, the classification of nearings of higher order requires much more complex calculations. For local nearings, they were realized in the form of a new GAP package called local NR. The author of the package is Yaroslav Sisak, and we are contributors of this paper. The new version of this package was, in 2024, not 25, sorry. We provide, I think, in this year a new version, but I'm sorry, it's a bit mistake. It's a current version, not yet distributed with GAP, contains 37,599 local nearings of order at most 361, except orders 128 to 256 and some of orders 32, 64, and 243. And I really hope that today we will present you some new results with classification of local nearings of order 128. In our paper of 2024, it was shown that on each groups of order P in power 3 with P more than 2, there exists local nearing. Moreover, lower bounds of the number of local nearings on the groups of order P in power 3 are obtained. And we study elementary abelian groups of order P in power 3 as the additive group of local nearing. The next natural step is to investigate groups of order P in power 4 as the additive groups of local nearings, and we consider two cases. First, it's with nilpotent class 2, and a second step is nilpotency class 3. And we have two papers in these directions. It's last year and this year. And so the following assertion is well known. It's, for example, you can find in paper of Clay Malone, 1966, the exponent of the additive group of a finite nearring R with identity I is equal to the additive order of I, which coincides with the additive order of every invertible element of R. And so we use this definition, but now I provided. A nearring R with identity is called local if the set L of all non-invertible elements of R forms a subgroup of the additive group and any field if L is equal to 0. Finite local nearings with a cyclic subgroup of non-invertible elements are described in our paper in 2013. And the following theorem was proved by Maxon. If R is a finite local nearing, which is not a new field, then order of R is less than order of its subgroup of non-invertible elements in power 2. And as a consequence, we have the following result. Let R be a local nearing of order P in power 4 with a non-abelian additive group and is not a new field then the subgroup of non-invertible elements L is the non-cyclic group of order p in power 3 or p in power 2. Due to Onishuk Isisak 2013, let G be a group and G be the set of all its endomorphism, which can be considered as a semigroup with respect to the composition operation of endomorphism. For each G from group G, we denote by G, and G is the set G alpha, where alpha is from semigroup of endomorphisms of G of all images of the element G with respect to endomorphisms of semigroup and G. And we have definition. A group G is called endocyclic if it contains an element G with this equality. It is clear that in this case, G is an element of maximum order in G. And we recall the following definition: a finite non-abelian group whose proper subgroups are abelian is called a Miller-Maryna group. So groups of nilpotency class 2 of order p in power 4. We use this notation n y in brackets, in square brackets, where b is the ith group of order n in the smaller groups library in the computer system gap, and we denote by c sub n the cyclic group of order n. And so it is easy to exercise, for example, in gap to get the following assertion. There are 6 groups of nilpotency class 2 of order 2 in power 4. It means that it's of order 16, which are, and here we have 6 groups. This is symbol of a semi-direct product. This is a symbol of a direct product of this group. So the following theorem contains the classification of groups of the nilpotency class 2 of order p in power 4, where p is a node prime. Now we use classification per side, but in some other version. So there are 6 groups of the nilpotency class 2 of order p in power 4, where p is a node prime, which are G1, G2, and so on, G6. And so we describe each of these groups, whether these groups are additive group of local nearings. So, as was mentioned about both a library of all non-isomorphic nearings with identity of order up to 31 are contained in this package Sonata. And so all non-isomorphic local nearings of order 16. It's understandable, yeah. And so, oh, sorry, I repeat the notation. The following groups of the nilpotency class 2 and only they are the additive groups of local nearings of order 16. And so we have 4 non-abelian groups. This notation means that this is a group of order 16 and it's a 4th type of isomorphism in a small group library in a package gap. Let n of G be the number of all non-isomorphic local nearings R whose additive group is isomorphic to the group G. So we have such information about the number of local nearings in such groups. So we have 4 groups and 4 numbers of these local nearings. And the groups G1, G2, and G3 from theorem 2 are Miller-Maryna groups. And due to our papers, we can conclude that there exist local nearings whose additive group is isomorphic to group G3 as a consequence there does not exist a local nearing on the additive group G2. And so this is like illustration. We can conclude group G1. This is a group of exponent p in power 2. And according to our paper, this is there exists a local nearing whose additive group is isomorphic to G1. And so we provide a multiplication formula for local nearings on this group. And this is example for order 3 in power 4. And here we provide one of the following multiplication, which guarantees that this structure is local nearing. And from the package local NR and the node repository, where we save constructed local nearings, we have the following number of all non-isomorphic zero-symmetric local nearings on group G1 of orders 81 and 625. And so this is classification of this. It's non-isomorphic, it means nearing, local nearings. What about group G sub 4? Let R be a local nearing whose additive group is isomorphic to group G sub 4. Then additive group is of such structure with the following relation, and in particular each element X from nearing R is uniquely written in the form X, we have such linear combination with the coefficients X sub 1, X sub 2, and X sub 3, and X sub 4 for coefficients we have. And I only provide for this case some results. As you see, this is really not short, and that's why only for this group we provide, okay? If A coincides with the identity element R, then X and Y in has such linear combination, and the index of subgroup of non-invertible elements in R is equal to P, and XB and XD is such XB and XD is such linear combinations, then we have such multiplication in our nearing with identity R. And moreover, for the mappings alpha, beta, and so on till T, the following statements hold. And we have 9 statements. And this lemma guarantee us that we really can construct local nearings on such group. Let R be a local nearing whose additive group of R is isomorphic to G4, and index subgroup of, and we have X and Y linear combination, and then the mappings beta and so on from multiplication a star can be one of the following. And these two types of mappings guarantee that we really construct local nearings on such group. And from our package local NR and the node repository, we can provide such classification in groups of order 81 and 625. And so the same situation with the G sub 5. I will not tell you a lot about this case, but the main theorem that for each odd prime P there exists a local nearing R whose additive group is isomorphic to G5. And here we provide the classification for order 81 and 625. And what about group G sub 6? We have questions about this group. G sub 6 is not endocyclic, and we have conjecture there does not exist a local nearing whose additive group is isomorphic to G sub 6. Really, we haven't get any examples of existing local nearings or nearings with identity on non-endocyclic group, And so we really hope that this conjecture is true. And so this is about class nilpotency 3, but I miss this, and I want to provide you classification of local nearings of small orders. So, and a computer program verified the nearings obtained in our examples are indeed local nearings are deposited in GitHub, and this is a link for this algorithm. And now Iryna continue our talk. Thank you. The data library of local nearings of small order. There are 51 non-isomorphic groups of order 32, from which 19 are the additive groups. We have theorem with Prokopovich. The following groups, and only they are the additive groups of local nearings of order 32. And we have 19 groups and number of local nearings. About the group 45 and 51, we don't know exact number, and now we continue our calculation. There exist 267 non-isomorphic groups of order 64, and from which 53 are two-generated groups, and only 24 of these groups are the additive groups of local nearings. And we have theorem. The following two generated groups are the additive groups of local nearings of order 64. And we have a number of local nearings. There exist 2,328 non-isomorphic groups of order 128. From which 162 are two-generated groups, 5 groups are of exponent 64, 18 groups are of exponent 32, 65 groups are of exponent 16, and 72 groups are of exponent 8, and 2 groups are of exponent 4. And we have the next result, following result. The following two generated groups of exponent 4, and only they are the additive groups of zero symmetric local nearings of order 128. And we have not exact number. The following two generated groups of exponent 8 are the additive groups of zero symmetric local nearings of order 128. And we have these groups, but exact number we don't know, in progress. We have question. Are the following two generated groups of exponent 8 the additive groups of zero symmetric local nearings of order 128? About this group, we don't know anything, but about this group, it now calculated in a server, and maybe this group is a additive group, but it is a question now. And the following two generated groups of exponent 16, and only they are the additive groups of zero symmetric local nearings of order 128. This one group, we have information about exact number of local nearings, but zero symmetric. And this group, exact number. There exists this number, zero symmetric local nearings on two generated additive groups of exponent 32 of order 128. And we have all exact numbers. There exist 124 zero-symmetric local nearings on two generated additive groups of exponents 64 of order 128. And we have this number. The obtained result will find application in the study of non-distributive structures and their classification. Local nearings are closely related to braces, which give solutions to the combinatorial Young-Baxter equation. For example, this paper in 2019. A result from the theory of nearing, in particular local nearings, can be used in the construction of cryptographic schemes and coding. For example, the name very difficult, and 3 papers. In the references I show. And the reference. Clay Malone, Clay Doyle, Clay, Maxon, House, fundamental paper, Maxon, our papers, Invoiced, Sonata, Gap, our package, some our papers, the node database, Rump paper, and the papers of application, 3 papers. Thank you.